Hey guys, today we're looking at question 174 on LeetCode. The question says, the demons have captured the princess and imprisoned her in the bottom right corner of a dungeon. The dungeon consists of n by n rooms laid out in a 2D grid. Our valiant knight was initially positioned in the top left room and must fight his way through the dungeon to rescue the princess. The knight has some initial health, and if at any point this health drops to 0 or below, he dies immediately. Some of the rooms are guarded by demons, represented by negative integers, so the knight loses health upon entering these rooms. Other rooms are empty, represented by 0, or contain magic orbs that increase the knight's health, represented by positive integers. To reach the princess as quickly as possible, the knight decides to move only rightward or downward in each step. Return the knight's minimum initial health so that he can rescue the princess. We're given a sample instance of the problem. It's a 3 by 3 grid. And the solution to this problem is 7 points of health. That is, if the knight follows the path denoted by the black arrows, he only needs 7 points of health to reach the princess. And we can verify this as follows. So initially with 7 points of health, the knight will lose 2 points of health upon entering the dungeon. And this will be followed by the 3 points of health in the next room. He'll gain 3 points of health in the top right room, followed by 1 point of health, and then finally we'll lose 5 points of health in the room with the princess. So the 7 points of health is the minimum. There is no other path the knight could take where he could start with less than 7 points of health and make it to the princess. So with the problem definition aside, let's jump straight to the solution. Our solution is going to be one that employs dynamic programming. So the kind of strategy I use with dynamic programming is to first define my subproblem, and then define our base cases. So what do I mean when I say define a subproblem? Basically, the question we have to ask ourselves is there a way we can divide this dungeon up into smaller mini dungeons so that solving these mini dungeons yields a solution to the overall dungeon? So consider this smaller dungeon that I'm highlighting. It's a 3 by 2 dungeon. And let's ask the question, what is the minimum amount of health the knight needs to reach the princess from this starting square? And the starting square is index 1, 2 of the original dungeon. So I'll formulate the problem as follows. What is the optimum amount of health the knight needs to reach the princess starting from grid index 1, 2? Now let's consider the second mini dungeon. This time we have a 2 by 3 dungeon. And very similarly, let's ask what is the optimum amount of health the knight needs to reach the princess from his new starting square, which is grid index 2, 1 of the original dungeon. In the same fashion, we could formulate the problem as opt of 2, 1. And that is, what is the optimum amount of health to reach the princess starting from grid index 2, 1? So let's now zoom out again and look at the overall problem. Our original problem was what is the optimal amount of health the knight needs to reach the princess starting from the very first grid of the dungeon. That was grid index 1, 1. We can formulate that as opt of 1, 1. Now is there some way we can link opt of 1, 1 with opt of 1, 2 or opt of 2, 1? More formally, can we link opt of 1, 1 to some function of opt of 1, 2 or opt of 2, 1? Well, we know the knight has to make a decision, right? He's got to go either to the right or down the page. Suppose for a second that we've clearly defined opt 1 of 1. What are some facts we can state about opt 1 of 1? Well, we know we're going to start in grid index 1, 1, and in this room we're going to immediately lose 2 points of health. In other words, on leaving grid index 1, 1, the amount of health we'll have remaining will be opt 1 of 1 minus 2 points of health. And provided opt 1 of 1 was truly the minimum amount of health required for the knight to reach the princess, opt 1 of 1 minus 2 is then the minimum amount of health required for the knight to reach the princess from any of the neighboring squares of grid index 1, 1. So writing this out, we can say that opt 1, 1 minus 2 is either opt 1, 2 or opt 2, 1. Wondering which of these two possibilities it is, it's the one that yields the minimal health overall. So to incorporate the minimum, we can just rearrange this expression as follows. and wrap the entire thing inside of a minimization function. And just for clarity's sake, I'm going to turn the positive 2 into the negation of a negative 2. So now we have our function for opt11. And not only that, we've defined opt11 as a function of opt12 and opt21. So now I'd like to express this function not only for opt11, opt12, or opt21, but for any ij index within the dungeon. More specifically, can we come up with an expression for opt_ij? Well, let's use opt11 as a reference and see if we can. So opt_ij would then be the minimum of opt of ij plus 1 minus, now a minus 2 here is simply the value stored in the dungeon whose room index is ij. Writing that out, we'd get dij, assuming the dungeon is stored in some matrix D. And our second expression, very similarly, is opt of I plus 1j minus dij. So let's hone in on both of these dij expressions. What do these mean? Well, in a given room with a demon, we're going to lose minus x points of health. This means, in the context of the expression, that we need to add x points of health to be able to facilitate this health loss. Conversely, suppose we have a health potion which provides us x points of health. We're able to reduce our minimum by a further x points of health, knowing that the potion is going to give us those health points. However, this only works to an extent. Suppose, for instance, the amount of health points a potion in room ij provides is more than the minimum amount of health required to reach the princess from any neighboring square. That is, d of ij is strictly more than opt of ij plus 1 or opt of I plus 1j. I'll just use opt I plus 1j to illustrate the point here. If dij is greater than opt I plus 1j, that would mean that the above expression would lead to a negative number. And clearly we can't allow this to happen, as the knight needs to have at least 1 point of health. Knowing that the knight needs to have at least 1 point of health, we can replace the dij expression with the minimum of either dij or opt of I plus 1j minus 1. And this guarantees for the case where the room has a health potion that if the health potion provides an excess of health points, that we only need to reduce the knight's health to a single health point. Also notice that in the case where the room has a demon, that the dij expression will always be a negative number, whereas opt I plus 1j minus 1 will always be a positive number, and therefore dij will always be the value resolved from this minimization. So going back to our original expression, let's replace the dij term with the updated one. And so here we land on our final subproblem definition. The next thing we want to consider are the base cases of our problem. We know that on every subsequent execution of the subproblem that we are incrementing either the j term or the I term. So in some way, our base case will be linked to the dimensions of the dungeon. I'm going to go ahead and draw a box to represent the grid of our dungeon. It has I rows and j columns. If we were to allow our program to continually call the subproblem, we can see that at some point we would begin to recurse into these regions outside of the bounds of the grid. That is, when the j value was more than the number of columns or the I value was more than the number of rows of our dungeon. Now we want to prohibit this from happening, so these are two of the base cases we can start with. Now I mentioned before that we can assume we have access to some matrix D, which is our dungeon. Using this, we can define our first base case, which is if our j value is more than the number of columns of the dungeon matrix, or if our I value is more than the number of rows of our matrix, we can immediately exit. Now when we exit, we still have to provide some kind of a value. If we know that we're in an area that is unreachable for the knight, we could equate this as to being somewhere that's very costly for the knight to be in. And we could do this by returning a very large integer. The second base case is when we arrive at the princess, that is the bottom right square of the dungeon. In terms of indices, this is the room that's indexed at the number of rows of the dungeon and the number of columns of the dungeon. When we arrive in this position, we're no longer able to recurse onto any of the neighbors. as there are no neighbors left. Arriving in this room is equivalent to asking what is the minimum amount of health a knight must have to reach the princess if the dungeon is a single room. And clearly, the amount of health a knight needs to have is simply the amount of health to survive in that single room. So, for instance, if there's a demon that causes minus X health points of damage, we need to have X plus 1 points of health to survive the room. On the opposite end, if there's a health potion that provides X points of health, then we know we can arrive with at minimum 1 point of health in this room, because there's no reason for us to lose any further health on entering this room. We can describe this base case as follows. So just restating it, if j is equal to the columns of D and I is equal to the rows of D, we can simply return dij plus 1 if dij is less than 0, i.e. if there's a demon in the room, or we can simply return the integer 1. So with these two base cases defined, as well as our subproblem definition, we're now ready to go ahead and begin coding our solution. Alright guys, here we are in the LeetCode user interface. We've got an empty method called calculate minimum HP. The first thing I always like to do is create my own method, which I call from the parent method. I'm going to call the method opt, the same as the opt that we defined in our subproblem definition. Just reiterating, our opt is for a given index ij, the minimum amount of health the knight needs to traverse to the princess if he were to begin from grid index ij of the dungeon. And again, I've defined the grid as a matrix D, D standing for dungeon. And our more numerical definition of opt ij was the result of two recursive calls to subproblems related to opt ij. That was opt I of j plus 1 and opt I plus 1 of j. Let's not worry about the function signature just yet, and instead think about the guts of this method. Namely, I'm thinking two sections. The first we'll call the base cases, and the second will be the recursive step. Now we've already identified the two base cases we're talking about. The first one is if we're outside of the bounds of the grid, that is, if our I or j index is more than the rows or the columns of D. In this case, we want to return a very large number. Our very large number is a member variable I've called inf, and I've just set it to 9,999. Just a note, in C++, arrays use zero indexing, so if we want to check whether the indexes are outside the bounds of an array, we don't check whether I or j is more than the rows or columns, we check if it's more than or equal to the rows of the columns. The second base case was when we arrive at the princess, and that occurs when our indexes I and j are equal to the number of rows and number of columns of D. And again, in C++ lingo, that means when the indices are equal to the number of rows minus 1, as well as the number of columns minus 1. We had two kind of subcategories here. That is, if the princess's room included a demon, then we had to make sure that the knight has enough health to be able to take the damage from this demon. And the other case was if the room had a health potion. In this case, the knight only had to have its minimal health, which was 1 health point. And that just about wraps up the base cases. Let's have a look at the recursive step. I'm going to define a temporary variable called r, standing for result. And this is what we'll return. Now r is the value of opt ij. And there we go. Now the last thing we need to do is just fix up our function signatures. And finally, I'm calling our method opt from the parent method, and I'm setting our initial index to 0, 0, where the knight starts on the top left corner of the dungeon. Alright, so after a few teething issues, it looks like we're passing 2 of the base cases. Now let's submit it. Alright, so it looks like our time limit's been exceeded. This is a very classic issue when dealing with dynamic programming problems. The solution to this is typically to incorporate memoization inside of your method. To do this, we'll introduce a hash table, which I'll call memo, at the very top level of our solution. Let's also pass this variable memo into our opt method and add it to our function signature. For any subsequent calls to the same opt ij, where I and j are the same, we can simply pull the pre-calculated result from this data structure memo and output that, rather than having to undertake all of that computation again. So let's first define our key. The next thing we want to do is check whether we've already stored this result from a previous recursion. And if so, we just return this result. Otherwise, we can go about executing the method as usual. We just need to make sure at the very bottom of the method, before we return our value r, that we store this in our hash map. Now let's run that again and give it a go. All right, seems like it's also passed the test case where we exceeded the time limit. Let's try to submit again. So our submission's been accepted. Thank you guys for watching. That's the end of the video. See you in the next one.